Okay, I think it's time. Welcome to this session of the interesting upcoming low latency, concurrency, and parallelism feature session from especially the last three C++ standard meeting. The three of us have always been working very closely in low latency, concurrency, parallelism ever since we've been together at IBM, and this has continued. My name is Michael Wong, and along with my colleagues, Paul McKenney and Michael, we're going to be talking about these three things. We're going to cover, we picked these because they are interesting. Some of them have a good chance of making it into a standard in the future. And they're bite-sized enough that they're good for a presentation. So I'm going to talk about SIMD. Maggot is going to talk about concurrent queues. And Paul is going to come up and talk about lifetime endpointer zap. Now, the first one is already in C++26. That's going to get being voted on right now. Okay. The second one, concurrent queues, has made a lot of progress after being stalled for many, many years. And maybe it will enter the standard in some future time. We think that there's a lot of room for growth because concurrent queues can be a big mess. You know, there's many different kinds. And we welcome anyone who has suggestions about how to improve it, or even if about their own concurrent queues. And lifetime endpointer zap, I know you've been hearing this story since 2019. We're finally coming to an end. And the end sounds like it's going to be something that is doable and understandable for a lot of people. Okay, so let's get into it. Okay, so how many of you, I'm going to talk about SIMD. How many of you have written platform-specific SIMD code? Anybody written platform-specific SIMD code? Now keep your hands up if you enjoy maintaining it across many different architectures. The keyword there is you enjoyed maintaining it. Okay, a lot of hands went down fast. For years, our CPUs have had these powerful parallel processing capabilities, but accessing them in a standard portable way has been difficult. With C++26, that's about to change. And today, we're going to explore how C++26 stood SIMD finally frees us from the pound if that game. Now here, I had to really squeeze it down. I've been working with SIMD for years because I used to work at IBM, then I worked at Intel, and then I did RISC-V for a while. So it's 1997, MMX, SSE 1999, UltraVec, that's when I started. Yes, I'm that old. SSE, that was the PowerPC generations. And then you have the SSE 2, 3, 4, then ARM came in with Neon, and then Intel AMD combined to create what's called AVX, AVX2, finally AVX 512 as being the most recent. And then, of course, in the most recent variants of that is the one from RISC-V, which is called Scalable Vector Extension, which can scale from 128 to 2048-bit. Fundamentally, the concept of SIMD has evolved significantly over the past few decades. With each new generation, there's a widening of the vector registers and adding more powerful operations. SIMD library is this that we're going to talk about for the standard, is going to be designed to provide a portable abstractions over these different hardware instruction sets. So if you've ever found yourself staring at a critical loop, just hoping the compiler would vectorize it, you know the pain. Auto-vectorization is a fantastic technology, but it's fragile and offers no guarantees. On the other hand, diving into platform-specific intrinsics leads to an unreadable, unportable mess of pound if-defs. We've always needed a better way. With C++26, that way is here, stud::SIMD. Offers the promise of writing clean, standard, and portable C++ that gives you the explicit control over the powerful SIMD hardware that's inside every modern CPU. I know, I get it. Most of the time I come up here for the last 10, 15 years, I talk about software parallelism. For the first time, I'm actually driving home that there's hardware parallelism in your CPU, and most people are not accessing. All right, so here's the core principle. The core principle of SimD is simple. It's just element-wise operations. You create a SimD object which holds multiple values. When you apply an operator like plus or multiply, that operation happens on every corresponding element in parallel. Here we multiply, so fundamentally the SIMD type behaves like a scalar, but every operation is on to all the elements at once. These are what typically called the lanes. We have std : SIMD of t, which gives you a vector of n elements of t. We have std SIMD underscore mask, which gives you a vector of n booleans, typically from a comparison. So the C++ code here, we multiply all four prices by the tax rate all at once. The key takeaway there is that you write code that looks familiar, but it expresses data parallelism. Comparisons are also element-wise, and they don't return a single bool. They return a SIMD mask, which we'll use for conditional logic. Here in this case, we look at which one of these is expensive. The first two are false, they're not expensive. The last two at $39.99 and $49.99 are very expensive, especially in today's world. All right, working with different data types is common. The most important rule is to keep the vector width or the number of lanes consistent. And the key to doing that, ladies and gentlemen, is the rebind underscore SIMD is your tool for doing this. It lets you create, for example, an integer vector that has the exact same number of lanes as your floating point vector. This is critical because operations between vectors of different sizes are compile time errors. By using rebind underscore SIMD, you ensure your types are compatible, allowing for efficient conversions and operations without performance penalties. So with coherence is the key to SIMD performance. Use traits to create compatible SIMD types. So you have SIMD of t, or you could use native SIMD of t, which just automatically use the compiler's recommended native width for type t. And then you can say further, you can say SIMD of t of n, which allows you to specify a fixed width of n. Or you can further say rebind underscore SIMD of t of u and v, which change the element type from v's type to u, but keeps the same width. That's the real secret sauce here, okay? So now we get into one of my favorite topics, branchless computations, which is branchless control flow with SIMD select. When I was a young programmer, one of the first things we were told was, don't use the if statements in a SIMD clause. And well, you could. If you did, that would be very bad. So you can't use it because what it would do is it would force all of your parallel lanes down a single path. The solution, therefore, is what's called branchless computation. So the traditional if statements create branches. So we use masks to fake conditional logic without branching. This is the SIMD underscore select clause. The pattern is, first, create a mask with a comparison, then use SIMD underscore select. It's the SIMD equivalent of the ternary operator. It's just a question mark colon operator. It takes the mask and two values, and for each lane, it selects from the true value if the mask is true, and the false value otherwise. This happens without any code branches, keeping the hardware fully parallel, blasting all the way through. So the next thing we got to think about is reductions. This is very, very common. Even in my days when I was CEO of OpenMP, we were trying to figure out how to create the reduction operator, and it has exactly the same syntax. So what happens in your workflow? After you've done your parallel work, you often need to aggregate the result into a single number, accumulate it. These are called reductions, or otherwise horizontal operations. Std reduce is going to be your primary tool for doing that. This is a classic example is the dot product. You multiply two vectors element-wise. That's the vertical operation, yeah. Then call reduce on the result to sum all the products into one scalar. That's the horizontal operation where you do across. So the library also provides other common reductions like reduce min, reduce max, as well as helpers to mask, for mask like any of to check if any lanes was true. So here you can see all the typical reduction of the reduce, which is a general purpose tool for some product, reduce min for finding min max, all of, any of, reduce count of the mask, which stands for analyzing mask. All right. Getting close. The syntax is actually pretty simple and very sparse. The last thing I want to do, yep, I think this is the last thing. Second last thing I want to do is the memory. Now you got to figure out how to get data in and out. We're just talking about basic computer science problems here. So your data usually starts in a standard container like a vector or span, and the typical SIMD workflow is to loop over the data in chunks equal to the SIMD width. The library provides loads and store functions to move data between memory and SIMD objects. Partial load is important because it safely handles what happens when you're at the end of an array, where you might not have a full vector's width of a data. You need partial load. Make sense? So all this is just efficiently loading from and storing to memory in vector-sized chunks. You've got loading for SIMD unchecked loads, for full chunks, partial loads for when you don't have enough. Storing, SIMD unchecked store and partial store. Flags, give it to the compiler performance hints, like is it aligned? Can you convert? Things like that. All right. So this is the last thing, and it's a superpower. It's one of the library's killer features. You don't need to find special SIMD versions of math functions. The entire CMath library is overloaded. Sine, cosine, square root, they all work out of the box with SIMD types. That's magical. That's a superpower because it means you can translate complex mathematical formulas directly into readable, high-performance C++ code. Here, we're verifying a trig identity on an entire vector of numbers at once. The result is a vector of ones, providing that the identity holds for all our data points. So, does it work? Absolutely. The benchmarks show consistent, significant speed up across different domains and hardware platforms using the exactly same code. This is from the paper. Image blur, 5 times faster. Matrix multiply, about 5 times faster. Ray tracing, 6 times faster. Audio processing, 4 times faster. But there's an important caveat, power. SIMD units, especially wide ones like AVX512, are power hungry. Running them flat out can cause your CPU to heat up and automatically slow down, throttle down, to stay within its thermal limit. It's just called thermal throttling. Now, this is really bad because not only is it thermal throttling your SIMD units, it's thermal throttling all your other instructions as well too. You can manage this, however, if you find your application is throttling, which will happen if you run SIMD flat out for a while, not like for a blip or something like that, some toy test case, you do have the control to request a smaller vector width. That is the answer. That is the solution. This lets you trade peak instruction power for a higher sustained clock frequency, which can sometimes be a net win. So one of the big questions that people have always asked is, how do you compare CPU SIMD and GPU SIMT on SIMD? Now, I come from the land of writing code for GPUs, heterogeneous computing. So I can definitely give you a perspective about how they're the same and how they're different. So a quick but important clarification. SimD is a CPU technology. While GPUs also use SIMD principles in the hardware, their scale and the software programming is called SIMT on top of SIMD. SIMT stands for single instruction multiple thread. Now, these are fundamentally different. CPUs are about using a few smart cores to reduce latency. GPUs use an army of simple cores to maximize throughput. So the key takeaway there is that SIMD is the right tool for accelerating tasks on the CPU. For GPUs, you're going to have to go to some dedicated framework. We call them CUDA, SICO, which is what I used to be the chair of, HIP. That's why you need those massive frameworks. So at the hardware level, you're right. The computational units of GPUs cores are indeed SIMD units. Very similar in principle to those that are in CPUs. The SIMT model is the programming interface that's built on top of this underlying SIMD architecture. So let me put it in some analogy. CPU SIMD makes fast cores faster. GPU SIMDs uses many slow cores to achieve massive parallel throughput. Depends on your use. The answer in computer science is almost always it depends. They are not competing technologies, but rather complementary tools designed to solve different kinds of computational problems. The CPU analogy here, let me try it. Think of a master chef in the kitchen. The chef is incredibly skilled. He has basically a powerful CPU core and can chop 4 carrots at once with a special knife, a SIMD instruction knife. I'd love to see this on Amazon someday. 4 carrots chopping at once. They can quickly switch between complex tasks, boiling some water, and versus making lasagna, I don't know. I'm not a cook. And are not slow down if 1 carrot needs to be handled differently. The GPU, however, think of an assembly line with thousands of workers. A supervisor might shout 1 command, turn the screw, and all the workers do it simultaneously. The line is incredibly efficient if everyone does the exact same thing. But if 1 worker needs to follow a different instruction, the entire group has to wait, significantly slowing down the overall process. This proposal is designed for and optimized exclusively for CPU SIMD, and it's not intended to serve as a direct programming for GPUs, which both architectures exploit. While they both exploit data parallelism, the execution models are too different for a single abstraction like SIMD to efficiently target both. And these are some of the reasons why that architecture is different. So if you've experimented with the Parallelism TS, you'll find the final C++26 version a significant improvement. The API has been simplified. Complex ABI tags are now hidden behind easy-to-use aliases. The confusing where clause is gone, replaced by a much clearer SIMD select function that I talked about. Names are more consistent, and type conversions are safe by default. It's a polished, powerful, and final product. Here are a few best practices. Structure your main loops to iterate in chunks of the vector width. Use rebind_SIMD to create sets of types that work together seamlessly. Always prefers SIMD select over branching. It's as if I haven't been that horse bad enough. But I will. I will keep beating it. On the flip side, be careful not to mix incompatible widths. The compiler will stop you, and be aware of preconditions, especially for functions like reduce min index, which requires at least 1 true element in the mask to be valid. So let's put it all together. This function applies a gamma correction to an image. It follows the classic pattern. It loops through the data in SIMD-sized chunks. It uses SIMD_partial load to safely grab data. Even at the very end of the span, it uses the overloaded POW function from CMath to apply the formula to all the pixels in the chunk at once. And finally, it uses SIMD partial store to write the result back. This is what real-world SIMD code looks like. It's clean, readable, and fast. Let's go through it a little bit line by line. Start with the function signature, gamma_correct. This defines a function named gamma_correct that takes 2 arguments, span float pixel, which is a non-owning mutable view of a contiguous block of memory containing floating point pixel values. Float gamma says the single scalar gamma value that's going to be applied to all pixels. Now we're going to do type aliasing and broadcast. The float v equals Stewart's : SIMD float says this creates a convenient type alias float v. The type SIMD float v, SIMD to float represents a vector that can hold multiple float values. The exact number of floats it holds, the float v size, if you will, is determined by the compiler based on the most efficient SIMD register size on the target hardware, usually 4, 8, or 16 floats. The const float v underscore gamma equals gamma says this creates a constant SIMD object named v underscore gamma. The single float value, gamma, is broadcast across all elements of v underscore gamma, for instance. For example, if float v holds 4 elements, v underscore gamma is going to have gamma, 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 gamma. This is required to use the gamma value in element-wise SIMD operations. Then we have the main loop. The for size I equals 0, pixel size I plus equals float v colon coincides. The last bit is important. The loop iterates over the pixel data, but instead of advancing one element at a time like I plus plus, it advances by a full SIMD vector width of I plus equals float v size. This allows the code to process the data in large parallel chunks. That's the secret. There's a little bit more below. Now we got into loading data. I'm not going to go to that, but notice that we have pixels subspan in that SIMD partial load that creates a new span that views the memory starting from the current index I. Then we have the partial load that reads values from that memory location into a SIMD object named pixel chunk. The partial in the function name is absolutely crucial because if the subspan at the end of the loop contains fewer elements than the SIMD width, the function is going to safely load only the available elements and initialize the remaining ones to 0. And this prevents reading past end of the array. Now we get into the magic of the parallel computation. In one line, I haven't said use std thread, I haven't used OpenMP, I haven't used anything. I said, POW. This is the one parallels processing. And POW is one of the many CMAT functions that are overloaded to work with SIMD types. It performs the POW operation element-wise, applying the gamma correction formula to every pixel in pixel chunks simultaneously using the corresponding broadcasted value from V gamma. Then I store the data, very common pattern. The partial store says, takes the SIMD object, corrected chunk, and writes its value back into the memory location pointed to by pixel subspan. And just like SIMD partial load, it safely handles the end of the array, making sure that it only writes the valid number of pixels per chunk. I am done. So the big takeaway, so to summarize, SIMD is a game changer for performance critical C++ low latency code, as long as you know the thermal caveat, and it's officially in C++ 2026, and it gives you the power to finally take control of your CPU's hardware in a way that's portable, type safe, and readable. Thank you very much. I'm going to invite my next colleague, Maggot Michael, up, where he is going to talk about, thank you, where he's going to talk about what's going on with concurrent queues. And there are so many of them. One too many, many too many, many too many.
Okay. Well, hi everyone. Can you hear me? Can you hear me? Okay, good. Okay, so I'll talk about the progress of concurrent queues in the committee. The proposal for concurrent queues started almost like 10 years ago, and it was a lot of like twists and turns along the way. In the past 1 year, there was so much progress happening that there were 9 revisions in 1 year, and the proposal progressed to SG1, the concurrency study group, and LEWG for the interface review, and the next step will be the wording review. So it made quite a lot of progress along the years, along the past year. So I'm going to go through what's the interface for the proposed concurrent queue and what features are supported and what features were dropped along the way. So there's a basic concurrent queue concept, and these are the basic operations are what you'd expect of like flavors of push that are copy, move, and construct in place, and they all return true if successful and false if the queue is closed. So that's kind of like the and they would block if the queue is full, and then I will talk more about what happens with closed queues that like when they're waiting push operations. The pop operation returns an optional T. The T is the type of the queue elements, and it's if it returns a null opt, that means the queue is closed. If it returns an element of type T, then that's a success of the pop operation. So these are kind of like the basic operations. For the more complex concepts of concurrent queues, there's a need for more complex status. So one of the big parts of this proposal is to provide a status enum of the queue states. And of course, one of them will be success. That's like the expected kind of case. But then empty and full and closed are what you expect. But then there are two more states that busy. These are might be internal synchronization. So you might, like some operation might be blocked on an empty queue, but then an element gets pushed in, but there's synchronization happening to actually complete that push. And then if you have a non-waiting operation, it needs like it cannot wait, and that's where we can have something like busy. There's busy async, which kind of I'm not getting into that too much detail, but it's probably will be dropped when there's more improvement in the executor interface. So it's a problem of you're doing a non-waiting operation that will unblock an async operation, but that will involve scheduling, and now you don't know if the scheduling will block or not, so you don't want a non-blocking operation to block, so you you return busy async, as in I can't guarantee that this will be non-waiting. Okay, so we'll get to these like states as we encounter them in the interface. So the next concept, the second concept is the concurrent queue concept, and that's kind of like it has a non-waiting interface. So for that you have different flavors of try push or try in place, and one flavor of try pop, and they all so the try push operations, they return a status. So they return success on like when they are able to push the element, and then otherwise they return different status if the queue is full or busy or async busy. The pop operation, the try pop operation, returns an expected. So that can be like it's either expected of type T, that's when it's successful, or the unexpected is a queue status. And these don't include success. They include the other, empty, closed, busy, or async busy. So this is like the non-waiting interface. Okay, there is the asynchronous interface, and that there's like async push and async in place for pushing, and async pop for popping elements. They all return senders. If you're I'm not going to get into that much detail, but if you're familiar with the sender-receiver model, they all return senders that will eventually call a completion signal or completion callback. And if it is successful, it calls set value. So the push will call set value void, as in, okay, it's successful. There's nothing to return other than, that's like a successful state. Whereas the pop sender, when successful, it will call set value T, like the element of type T. If the close is if the queue is closed, then there's these operations they call set error. And I'm getting to the closed queue in a minute, so to differentiate between the different cases. There's also support for cancellation. They would call set stops. Set stopped. Closed queues, there is a function close. It closes the queue. The model of like closed queue that is supported is just like once, and it never gets reopened again. I mean, along the way there were under consideration options to reopen queues, and that was found to be too complicated. Once a queue is closed, you cannot push in it, but you can still pop from it if it is not empty. And if there are waiting operations that were blocked on like an empty queue or a full queue, they will be unblocked immediately. And then if it is a push operation, it will return false, like as we remember from the basic interface. or if it is a pop operation, it will return null opt. So that's kind of the closed queue operations. One thing is about like failure handling. The proposal P0260, it takes the approach that nothing really is an error, as in like it's difficult to differentiate between what is like something like let's say a closed queue. Is that an error to like to say it's closed, or is that an and it's a failure of like pushing or popping, but it's not necessarily an error. So that's the approach taken by the proposal and this interface. So a pop operation that finds the queue is empty and closed, it would return empty optional. Push operation that finds a closed queue, it returns false. Try push returns the queue state. Try pop returns queue state as an unexpected if unsuccessful. Async push and async pop return senders that calls set error with a status. Then for exceptions, the queue may throw exceptions thrown by the element type T if it does throw on move or copy. It also can, if it allocates, it can throw storage allocation. As we'll see, the only type that's supported so far will be the bounded queue, so that will only be at construction time. And also synchronization exceptions depend on whatever the underlying synchronization technique. So let's say there's a mutex and deadlock detected, then it could throw that. Otherwise, it doesn't throw anything else. So actually, all what I talked about, there are like the concepts are they are not enforced except for the concrete type that will be supported, and that's for starters. There's one queue template that will be bounded queue, and it will support all the three concepts that I mentioned. And the constructor takes a maximum number of elements. That's like the bound of the queue. It may allocate. It will need to allocate at construction time, and that's the only time that it should that it may throw for like bad alloc. It will be so the element type is movable, copyable, but the queue itself will be not movable, not copyable. There was debate about the memory order of the queue operations, and the committee decided that it's more important to be intuitive for the first kind of the first supported concurrent queue than to be high performance. And the rationale here is that you could get unintuitive outcomes like this case of basically you have two threads. They are both pushing into two different queues, and you would get the outcome. Let's say it's pushing first in the main queue and then logging and say, I pushed the number one, and then another thread will say, we'll push two, and then it pushes two in that main queue. You might get an inconsistent result with acquire release memory order. That's taken from the paper or based on example from the paper P0387. That is like basically saying that to be intuitive, you have to support sequential consistency, and that's the approach taken by the committee for now. Personally, I think it's just as long as it doesn't shut the door closed on performance, then that's totally reasonable decision. So along the way there were a lot of features that were abandoned, and they would have complicated things a lot and probably blocked the way towards like higher performance. And yeah, so these were like allowing push front in addition to push and back and pop front, reopening closed queues. So it's kind of, you might have that happening concurrently. Lock-free in the strict theoretical sense. That's kind of a niche requirement that we don't want to impose that early on. There was streaming iterators where you can move elements from one queue to another, and the storage iterator was like in a quiescent queue. You would iterate over the elements. There was giving queues names, and all these got kind of consensus narrowed down to what I presented. So in summary, the proposal P0260 has made a lot of progress in the last year. And if things go if it gets adopted, it will introduce the status enum of the queue states, 3 concepts, exposition only, and 1 concrete concurrent queue that satisfies the requirement of all 3 concepts, supports sequential consistency, and it leaves the door open for high performance down the line. I'll hand it off to Paul in a second. Thank you. I'll take this.
Thank you. I have a favor to ask all of you. And it's something really important. I need you to make sure not to tell my wife that we spent many minutes flashing the audience. Anyway, I'm going to talk about lifetime in pointer zap. And I guess we've had some zapping here. And I need to find the page down button or something to advance the next. Oh, there we are. It just took its time. And it'll take time there. We'll get there. We've got 3 papers that we're talking about here. 2414 is the original solutions paper, and it is atomics and volatile. We'll talk about tightening invalid behavior. I can see it because I'm looking at the maggot's laptop. I'll tell you what, we can do this. All right, did anybody remember to bring the opera glasses? Okay, there we are. So can you broadcast it out to public media so the rest of the audience can see it? Oh, I can if you want to. No, did not. Well, anyway, I'm sorry. Okay, great. So the slides will be on the recording. We'll just, actually, this is also very appropriate to the subject matter. We're going to talk about pointers that flash in and out of invalidity. So you're getting practice with the previous things for that. And obviously somebody forgot to put a new call in here, and so we're kind of stuck for a bit. Anyway, we'll proceed along here and see how things go. The first question is, what is lifetime in pointer zap? You won't actually find that in the standard. They call them invalid pointers. Just to promote diversity, C calls them indeterminate pointers. The same concept with some slight variations, I'm sure. But the key point is, and this came as a massive shock to me. I mean, I first programmed in assembly language back in 1973. And so this bit about compilers making pointers invalid wasn't something I was prepared for. But the thing is, a pointer has bits, all right, and those are real. But if you have a program, which I could show you here, except you can't see it anyway, and it has a pointer p, and it allocates into p, so p equals new of something, and then we pass p to a function that might delete it, and then we allocate q, and we're going to, all right, and we're going to allocate from and put it in q. So we've got a load into p from new, we've got a function that might delete it, and then we have a load into q from a new. Now, if the function in between actually did a delete, it's entirely possible that the address of those two objects is the same. Okay? I mean, we could get back the memory we just freed. Could happen. But the thing is, the pointer consists of more than just the bits in memory. There's also something that in the, again, I don't think you find this as a standard yet, but in the communities around us is often called provenance. And the fact those two pointers came from different new statements says that the compiler can keep extra information in its own head, not in the bits, that say, hey, these pointers are different. So if you compare the pointers, if p equals q, p equals q, the compiler is within its rights just to say false. I'm not going to even load those pointers. I'm not going to compare them. They can't possibly point to the same object. They came from two different new calls. All right? That extra information the compiler is keeping about which new call generated which pointer is this provenance. And the trick is that when you delete an object, all pointers to it suddenly become invalid. And they've been zapped, if you will. And that happens instantaneously, which is another shock to a concurrency guy like myself that deals with laws of physics. So there are things that can go superluminarly through your machine, okay? And the compiler can make that happen for you. So, you know, figure out a way to convince the Nobel Prize Committee that that's real, and you're set. Now, why, again, for me this was a big shock, but the reason for it is that it enables a bunch of optimizations. In this case, if you compare two pointers and one of those pointers is invalid, the results are at best implementation defined. And the fact you're comparing a valid pointer to an invalid one means that even though the bits are the same, the compiler's within its rights to say those can't possibly be equal. So the fact that the pointer's invalid and the fact that any operation whatsoever, including like loading and storing it, okay, any operation on a pointer that is invalid is, again, at best implementation defined. Okay, so this allows some aliasing and some points to analysis and other things like that. And this is going to be a little more challenging because I'm showing the concurrent LIFO push algorithm for an atomic non-blocking stack. All right. Is Spock here? I need to do a mind build with the rest of the audience to help this out a bit. But in any case, this is a very simple, very powerful algorithm. Basically, it has it's a class, if you will. It has two operations. You can push an element, so you've got this element that's been gotten from somewhere, who knows. You push it onto the stack atomically, and you pop all of the elements off the stack so that you have a private copy of the stack, and now the stack is empty. It has a null pointer in it. So we're talking old school pointers here, right? And that means that the push, all it has to do is have a compare and exchange loop where it picks up the pointer to the head of the list, and then it puts it in the next pointer of the thing it's been handed, and then does a compare and swap. If that next pointer is still equal to the top, then we succeeded, and now we've got the element strung onto the list. If it fails, well, somebody else did something to the list while we were doing that, and we try again, load it again, and go around again. Pop all is straightforward. You just do an atomic exchange of null with what's ever in the head pointer. So the head pointer gets a null, and you have the list. Okay. Yeah. So we're going to do an example here, and I know you guys in the back can't see this very well, but it's probably better than me trying to hand wave these diagrams, all right? Maybe not much better, but you know, we take what we can get. Yeah, I guess this is, let's see, so if I do like that, that's probably the best angle. And now if I do like that, I can see it sort of. So what we're going to do is we're going to assume a simple compiler, and that may be just -O -1 or something, or maybe you're writing in assembly language, which is a fairly common thing. And what we're going to do is start with a stack like this one. We got the top pointer, and we got A and B there. And there's a task 1 that's going to push a new element C. And then there's another task 2 that's going to do a pop all, followed by a push of a new element D. All right? There we are. And so let's say that the task 1 does the first phase. So it's picked up the top pointer, it's stored it into C, so C now points to A. And it is also it's done those two things, picked it up and it's stored it to A. And so we have the diagram looking like this. The stack is still here, and task 1 points to C, which points to A, which points to B. So C is not yet on the stack, but it's all prepped and ready to go. Did I hit that once or twice? I hit it twice, at least twice. Let's try it just once this time. There we go. All right. Now, at this point, task B does a pop all. So the task 2 here does a pop all. So top is now null, and task 2 has the full list. Now, task 2 might naively think it's got it privately, but as we can see, the pointer from C followed A, and it points here. Now, that may seem really problematic, but that's okay, because if task 1 were to go and do its next step, the compare and swap would fail. This is a null pointer. It's not a pointer to A. And so it would say, and it would fail. It'd come back, load top again, get a null pointer, and life would be good. So this is really kind of okay. The compare and swap is going to save us. Unless task 2 now goes through and processes A and B and frees them, deletes them. And so they're on the free list here, and the pointer next from C now points in the free list. This is a really bad idea, as I'm sure most of you are very well aware. And we're coloring it red, which, if you've got really good vision, you might be able to see that, because it's invalid pointer now. So this pointer, the lifetime of the thing it's pointing to has ended, and so it's done. Except the pointer's still there. Now, task 2 was going to push D, so it allocates some memory, and it gets this A off the free list and becomes element D, same address. And that means that we have what we call a zombie pointer. The pointer to an element that's kind of come back from the dead in some sense. And Mag is going to help us out with the audience that's close to him, and thank you very much for that. So right now we've got this thing where D is the only thing on the stack, but we have this zombie pointer. Now, the thing is, compare and swap is defined to work only on the bits of the pointer. It knows nothing about provenance. So this compare and swap that this task is going to do is going to succeed. And once D gets on there, we got the zombie pointer still. We do the compare and swap, and we got a zombie pointer in there. That means the poorer process that pops all the stack again is going to find element C, and it's going to have a zombie pointer, an invalid pointer, that the implementation is permitted to do whatever it wants with. Implementation defined at best. And dereferencing an invalid pointer is probably undefined behavior. All right? So this is not good. But if you write in assembly language, it'd be perfectly valid. And from a bits and bytes viewpoint, it's a perfectly reasonable thing to do. This algorithm has extremely good forward progress properties. It's used really heavily, okay? So it'd be really nice if we could express it in C++. That's my opinion anyway. Feel free to disagree. I'll just laugh at you, it's fine. Okay, so how do we get here, right? Well, how could this happen? We got this thing that's used a lot, and we can't express it in C++ in any reasonable form. Well, in 1989, the C standard it was born, essentially, with this pointer invalidity concept, because they wanted to optimize. And C++, Bjarne explicitly wanted C++ to be like C, and this is part and parcel of that, right? So here we are. And then, but that was okay because both languages were sequential. There was no concurrency, so you couldn't express concurrent algorithms within the standard at all, much less the LIFO push. So life was still good, aside from people like me who were abusing C to write concurrent algorithms at that time, but that was my fault, not theirs. Anyway, in 2001, there was a defect report 260 that reaffirmed pointer invalidity and how it acted. And then in 2011, C and C++ got concurrency. And suddenly we had a problem. Everybody had a problem, not just me. And the problem is that we don't know when LIFO push algorithm was invented. Mag and Michael did some really impressive software archaeology and found a reference to it in a patent filed in 1973. Interestingly enough, a few months before I wrote my first line of code. So LIFO push has been around for a long time. It's not a new concurrent algorithm. Not only that, it's something that gets reinvented all the time. And people don't necessarily reinvent a nice template library. They often reinvent it open-coded in the middle of some other thing because they don't even think they're doing something abstract like that. And that may be a failure on their part, I won't argue. On the other hand, we don't have any way of finding all of them. We don't have any way of finding them and fixing them all. All right, so it'd be really nice if the standard could support that in the way it's naturally written. So we're making progress there. We're relying on a paper by Davis Herring. And the trick you've always been able to do is take a pointer, convert it to integer, and later on convert it back. And the compiler is supposed to, give or take a few bugs that still exist last I knew, is supposed to pick the object that that pointer might reference right now and make that a valid pointer to that object, regardless of what has happened between the time it was converted to integer and then converted back to a pointer. The problem is, as you saw, there was a bunch of stuff happening at the same time, and there wasn't any real way to keep the thing safe over that time period. So what Davis is proposing is that the compiler selects not just from the objects that exist right now, but also from objects that are created concurrently with that conversion to pointer operation. Okay? Now, if the object is created after, definitely after the conversion operation, the compiler is within its rights to do whatever. All right? And we tried the more aggressive approach last year and got shot down early this year. So we're trying again. All right, yeah, thank you. Yeah, that's what I'm talking about. Yeah, little excitement. As I said, you know, it's we were illustrating pointer zap in slideware. Okay, so we're basing some things on Davis's proposal, and one of them is that if you have an atomic or a volatile operation, it acts kind of like a conversion to integer and back. In other words, an atomic variable is kind of as if it was stored as an integer. It has the same semantics going in and out. And by the way, that includes the old reference. The old pointer is passed by reference to a successful compare exchange. The successful compare exchange doesn't actually change that pointer, it doesn't have to, but our request is that the compiler forget about any provenance it might have known about that pointer that was passed by reference to compare and exchange in the success case. All right? Now that doesn't solve the whole problem. We started with one paper and have had to split it for various reasons. The problem it doesn't solve is that you can't even load or store an invalid pointer. So it doesn't help for it to be okay when it gets to compare and swap, because you have to pass it as a parameter that involves at least conceptually a load and store. So we have to do something about that. So that's what this is doing. We want to tighten the implementation-defined behavior for invalid pointers. So if you have an operation that is not comparison, it's not arithmetic, and it's not a dereference, our request is that that be defined. In other words, if you have an invalid pointer and you load it and store it, it might still be invalid, but you get the same bits. All right? And that means we can pass an invalid pointer as an argument to a function like atomic load or atomic store. And if we have those three papers, Davis's and those two of ours, then LIFO-push becomes defined as you would normally write it, which is nice because we don't know how to find all the stupid things to change them in anyway, all right? Now, there was another paper, and that one is for non-concurrent applications. And there are things like debug things, where you use a pointer as a key in a hash map or something like that, because you're trying to figure out who freed it when you expected it to still be around. And now there are tools that do that automatically, address sanitizers and the like, but sometimes those are too much of a performance penalty, and you have to do it by hand for some little piece of your program. And making it so that we had a way of expressing that nicely is a great economic aid to people who are in the middle of the night trying to debug this stupid thing and don't need pointer infidelity to whack them over the head. Now, we can't do it with straight source code. We're proposing adding a launder putter-bits and a putter-bits template class that have the effect of maintaining a pointer and ignoring invalidity. You just get the bits of the pointer and no provenance comes into the picture. Okay, with that, if we can get the first three, as I said, LIFO-push becomes valid C++, no source code changes required. The last one allows us to use these, to have these debugging use cases supported by the standard with some source code changes, but something fairly natural, not storing things as integers and losing type checking and everything like that. With some luck, maybe we get this in C++29. We remain optimistic. This has been a long journey. We first presented this in 2019 here. With that, if Maggot and Michael would like to come up, we can field some questions. We've gone through SIMD and concurrent queues and lifetime endpointer zap.
Wow, some of from 2019 to 2029, some of us have changed career 3 times since that time. So we've talked about 3 things: SIMD, concurrent queues, and lifetime endpointer zap. Number 1 will be in C++26. And we're going to be voting for that actually right now. Number 2 and number 3 will likely be beyond C++26, maybe 29, maybe a little longer. That all depends. Are there any questions? Khalil? No questions, please.
Oh no, I just want to know about SIMD, and so for platforms that may not have as sophisticated SIMD, such as like being able to do SIMD operations on sine and cosine and those type of things, what would we expect from a library? Would it just simply fail at compile time, or would we get some other sort of behavior?
So your question is if a SIMD operation use sine or sine or unsigned?
Sine or basically, if you have any SIMD operation that isn't supported by your hardware, what does the standard say about how that will try to call it? Yeah.
Right, and there are quite a bit, right? Yeah. Obviously we have standard operations. The standard operations gets translated by the compiler to the local native platform, and if it doesn't exist, then it'll throw a compile time error.
Okay, so no like emulation or anything like that?
No way.
Okay, understood. Can I ask one more question about concurrent queues? Cool.
That's over here.
For a while, I've heard about concurrent queues, and there's one area that I don't fully understand. What is the value of the closing operation? So all the APIs have bool on them, so we have to check to see if the queue is closed. Why not just have them all be void and just remove the ability to be closed? So we don't have the ability to reopen them, right? So what's the close useful for?
The question about...
He wants to know why we have a close operation on the queue.
Oh, yeah. I mean, closed is useful in some cases because you want to signal that we're done. And usually people put like, an item that has a certain code. And this makes it kind of more formal as in closed. So it's kind of, there are operations where you're streaming things and keep extracting elements and just saying we're done. Don't try. You can safely close the operation that nothing will come after that.
Understood. Thank you.
There's actually SIMD question.
Theodore.
So
every year you ask me an impossible question. What would it be this year?
Well, at the beginning you asked, okay, how much did you suffer or something? How much did you like, making SIMD portable? The answer was for me actually wasn't a big deal until I got to the ARM, which has SVE.
Yes, and SVE. Yes.
So, and then I was looking at your slides and I'm like, okay, I don't actually understand how does that work with SVE. Looks like there's a static assert in there. There is something : size. SVE types are actually
you were going to ask that question.
Incomplete types. You can't do any of that.
Right, and it's because of the special characters of scalable vector extensions.
Yeah, they're all
and I know what it is
types.
because I helped design that in RISC-V. And I honestly don't know. I don't think it's going to be ready for SVE, to be quite honest, because it's the big thing about SVE is it's extendable and it's changeable.
And the same compiled code can have different widths at whatever it runs on.
So you notice that the SVE is the last entry on my long list, and I think I worked like 5 of those, right? But SVE, I designed it, but I never got to implement it, and I just don't think this proposal is going to be ready for that RISC-V extension yet. I could be wrong, but I need to look into it. But you're right.
Okay,
I knew you were going to ask me an impossible question.
I haven't dealt with RISC-V, but I ran into it on Grace.
Right.
Which has it.
Right.
And, okay, what do I do?
Yes, yeah. SVE is a bit of a different animal than all the other ones because all the difference is that all the other ones have always been fixed width. Okay, they don't say change in width, but SVE does, and that's the big thing in the RISC-V community.
I have two questions on SIMD.
Oh, no.
The first one, what happens if I set a size that is not supported by the architecture? Would I get a compile error?
So you can set a size that is not supported by the native.
Yeah.
You can. And I'm trying to recall through my mind through the spec whether it's going to give you a compile error, because it knows all the native sizes. So I have to check, but I'm pretty sure it will give you a compile error.
So it means that someone writes the code and I compile it on my machine,
Yeah,
even
that's
though it
why
might not
that's why
compile.
I'm putting a caveat. I'm not totally sure of this because I have to remember what the spec says. Okay, but it does. The thing is that if you don't say anything, it's going to give you the optimal size. But it also allows you to figure out what is the best. Whatever your optimal size is, what's divisible by it, right? There's only some n that's going to fit. It has to be all divisible by what is the maximum size. That's really the equation, right? From a compiler generator point of view, theoretically you could compute that and figure that out.
Yeah.
So why not, right? If you don't, there has to be some other reason that I haven't thought of.
Okay.
Okay, does that make sense?
Yeah, makes sense.
Thank you.
And the other question is, what is the performance penalty of partial load and partial store? Will the compiler unroll the last operation, or is it going to do a masked load every single time?
I believe it's going to unroll. Okay.
Is it not mandated by the standard?
No.
Okay.
It is not.
So
The standard cannot mandate unrolling unrolling the loop that way. Yeah.
Okay.
Yeah.
So you may get different performance with different compilers.
Potentially, yes.
Okay. Thank you.
Thank you.
Quick question about concurrent queues. I've implemented my own concurrent queues because I can't wait for C++29. But what I saw is that one of the things I'm glad about your proposal is the word close, because that's also the thing I'm using, not EOF, not something else, close. But what I'm sad about is that I don't see an operation of abort. In close, the pub can wait. The pub won't, if there are still elements, the pub can keep going. But with abort, I think that's also necessary, where even if there are still elements inside the queue, an aborted queue should not be allowed to have popped anymore. And of course, push shouldn't be allowed either. So is there any reason why abort is not?
Abort, in a way, you can think of abort as if you're using the async interface, you could do set stopped. So actually, you can do that in your implement.
Okay, so you can set there the stop token, for example.
There's you can do the completion signal to be set stopped.
Okay, got it. Yeah, thank you. Oh, okay.
Please use the microphone. We can't hear it on the recording.
I can give it to you.
Sorry, I'll just be quick. Just said it's part of the sender receiver framework. So as been said here, that basically the async operations are collaborating with that. So that's coming from there.
Got it.
Sorry, I lost my voice.
That's good to know.
I have a question about SIMD. Can there be side effect of partial load that fills 0 when there's not sufficient elements? So for example, if I have a vector of size 3, and let's say I want to do A by B, where A and B are two different vectors, and if we fill those last elements by 0, then there could be divide 0 by 0 kind of issue.
Okay, I'm going to have to echo back what I think I heard. A divide, you're talking about A divided by B?
Yes.
Okay.
And A and B are both vector of 3 size, which
Yes.
are loaded to SIMD.
Yes.
So the last elements we are like refilling with a 0, but
Oh, you got the last elements are infinity. Or
Second?
The last elements are something funny.
so the vector had vector is of size 3.
Yeah.
But when we are loading that vector to SIMD, and it's a partial load, so which means that we have to fill up the remaining elements
Right.
by 0.
Yeah.
But when you do A by B, I had valid elements in my vector for A by B to be valid for each element. But because we filled 0, it would be 0 divided by 0 on those SIMD.
0 divided by 0. The wonderful. Yeah, typically we go to with the standard these things goes to a NAND. Okay, there's no infinity. There's no way you can do 0 divided by 0. Okay.
Yeah, but basically my data was valid, but because I loaded in SIMD, it
Yeah.
became invalid. So
No, I get it, because you padded it with 0, because the
Yeah.
partial load padded it with 0, right? The spec, again, this is like really specific spec stuff I have to actually recall, and I really prefer to look it up. My professional belief is that it has to return a NaN whenever it has to do those last bits that are actually all padded as zeros.
got it.
Okay.
I think we're getting signal for
Yeah.
take it offline.
Oh, we got to take it offline.
All right.
So thank you very much.